Okay, good morning, guys. So in today's class, what we are going to do is that we are getting into filtering because last week was the time when we did rectification. So right after rectification, like the first half of the class, I had a chance to go to the shop and a few circuits for rectification. And then they also had to grasp some other pieces in order to apply a filter to the rectifier in order to obtain what you are going to see in the screen right now. So if you look at the oscilloscope right here at the bottom, you can see the following. Right at this point in time, I'm going to stop the simulation so you can see it. We have what is called here a voltage minimum and a voltage maximum. The reason why we have these two values is because this wave here, which is the pulsating wave, it has a minimum and max value. So if I hover, okay, so if you look at my cursor, and if I go right into here, okay, where I have the neutral plane, I would be getting a voltage which is very close to zero. Like this is not showing the voltage perfectly, but it shows that I have like minus 1.6 millivolts, which is pretty much close to nothing, okay? So that would be my minimum voltage. And why do I have a minimum voltage? Because this pattern, as you can see, which is the amount of voltage which is being registered at any of these loads, what happened is that when my voltage is rectified, this is coming from an AC signal. Okay, so, and I want to make this clear here by drawing an AC signal. So imagine like that AC signal is like this. It starts right at zero on the neutral plane, and then that AC signal goes to a max value, which is called a peak value. So this value here that says that is 39 volts, that's actually the peak value. It's also called on the oscilloscope max. Okay, that's the name that you are going to find on the actual oscilloscope. And today, when you are doing your project, you will have to go and find that max value using the measure function of the oscilloscope. So as I already mentioned, we are going to have to measure this peak value, which is the max value as measured by the oscilloscope. And then that AC signal is going to go all the way up to the max. Then it's going to go down and collapse until it goes back to zero. So it will go from 0 decreased, okay, 0 decreased, and 0 volts. It will advance to a 90 degrees of electrical rotation. And at 90 degrees, we have the max voltage. Okay. And then it will continue to advance this wave until we hit the 180 degrees mark. And when we hit that 180 degrees mark, then we have again zero voltage. So you can see now that because we are getting only the positive voltage, that's why that these 2 meters indicate that we have a max positive voltage, and also we have at this point in time a minimum voltage, which in this case happened to be zero, because we can see clearly here that the signal, okay, the pulsation, it always falls back to zero right here. Now, you may wonder, why is it that, I mean, that's pretty evident. That's very evident. Why is it I'm giving you this at this point in time? It is because once we use this little guy here, which is called a capacitor, which happens, we are going to be using a 500 microfarad capacitor. Once we do that, then we can cancel that 0 volt, okay? So we are going to be able to flatten the signal. So I'm going to rerun the simulation so you can see that now. And please pay attention to what's happening right here to your minimum voltage. Okay, the minimum voltage right now indicated by this simulation is minus 1.6. So I'm going to rerun the simulation. And then I'm going to close this switch. When I close this switch, we can see that the switch is going to bring online a capacitor, which is a 500 microfarad capacitor, which is connected in parallel with the rest of the circuit. So when I close my capacitor, I want you to notice what's going to happen to this minimum voltage here. And also I want you please to notice what's going to happen to the actual average voltage. At this point in time, that average voltage is being measured at roughly 28 volts. There's a little fluctuation because of the simulation, but it's voltage that average at 28 volts. So now let's close that switch and let's see what happens. So do you notice what happened as soon as we close the switch? As soon as we close the switch, you can see that the max and the minimum are equal because we don't have a minimum anymore, okay? So I'm gonna stop the simulation. Okay, so this being like this line right here at the bottom, I put like this little white line before. So I'm gonna make it bigger to make it easier to see. Like this line here that we have right here at the bottom, that is my 0 voltage line. I'll show you that once more. Before I close my capacitor, that was my reference line. Now, when I bring my capacitor in line, let's stop the simulation once more. You can see that I'm still here, okay, because this is a very large screen. It shows me like the before. This is the past, pretty much. All this is the past. And this is what's happening right now. And the reason why, once more, that the max and the minimum values are equal is because, well, the max value cannot change. It continues to be the same because that's going to be the max value that we are going to be able to obtain from this alternation, from this signal. However, the minimum value that used to be 0, because now we have a capacitor, this minimum value from that white line, from the 0 volts reference point, it is equal to the peak value as well. Okay, and you can see that that's what's happening like in the whole circuit. Now, as I am running the simulation, I'm going to show you, and that's going to be what you are doing in lab number 4 today. For those of you that already did it, it's going to serve as a refresher, you know, just to refresh what you did last week. Something that I want you to notice is that as soon as I turn on, or as soon as I turn on my first light bulb, which is my first load, I want you to notice what happened here, okay? And now we actually get a minimum voltage, which is different than the maximum voltage. And you may wonder, why is that happening? The reason why that's happening is because, in fact, from the 0 voltage line, now we had a voltage, I mean, like this perfect flat DC that we were having when we didn't have any load. Now, actually, we are going to have this capacitor discharging through that load. And because the capacitor is discharging through the load, the capacitor, you know, over time, it discharges through the load. But before the capacitor can finish discharging through the load, it gets recharged again. So, and the minimum voltage the capacitor will reach, the minimum discharge voltage for the capacitor in this case will be 35.9 volts. So it is important that you take the time and go through the slides about capacitor. We are going to cover a little bit of it today because that's something which is fundamental. But I needed to show you what's going on with this circuit because that's something that you are going to be doing in the shop actually. Any questions so far? Okay, so let's keep moving. Now, let's continue running this simulation and observe what is going to happen, okay? When I disconnect this load, everything goes back to normal in the sense that everything goes back to having a perfect DC signal. Now, if I engage, and I'm just gonna use this load because it's gonna give us a more dramatic result, then right on the screen, we can see what was happening before, okay? We were having a minimum voltage. Like if you follow my cursor, you can see that our minimum voltage when I had my 25-watt light bulb, which is still that rest of the signal, I was having a minimum voltage equal to 36.2 volts. Now, when I shut down the 25-watt light bulb, everything went back to normal. However, now when I turn on the 100-watt light bulb, because this is demanding more current, it's going to be discharging my capacitor at a faster rate. And because my capacitor is discharging faster, before my capacitor can start recharging again, the capacitor will go down, it will discharge to a voltage level which is equal to 24.5 volts, which is going to be my minimum voltage. So what's happening like behind the scenes is that we still have, like in the actual circuit, in this bridge rectifier, we still have that max and minimum going on, okay? So we still have that. I'm gonna open the capacitor pretty quickly so you can see it. Close it again. Okay, so we still have this voltage, and we still have that maximum and the minimum voltage dropping down to zero. So we still lose our full voltage through the bridge rectifier. However, now we have a little trick, which is that by using a capacitor, the capacitor is going to store energy in an electrostatic field. The capacitor will behave like a battery that we can charge instantly. Once we charge that capacitor, then the capacitor is going to hold the charge. And when this signal is collapsing and going to zero, then the charge, which is in the capacitor, that charge is going to start to go through the load. And the reason why we see this like crest and this little like discharging curve, it is because the capacitor is discharging, and right at this point when the capacitor is already at in this instance 29 volts, then again the signal goes back up and recharge the capacitor. So this is recharging the capacitor up all the way back to its max value, and then it is charging the capacitor. And this cycle continues to happen because of the amount of load that we have connected in the circuit. Just to end with this, at the end of the day, this is what's going to happen. Like if I decide to use an even higher load, then I'm going to be discharging the capacitor even at a faster rate. So when you may wonder, is there a solution for that? And the answer would be, sure, there is. If I decide to add even more capacitance, let's say that I decide to use, okay, 1 millifarad. And it seems that 500 microfarad is more than 1 millifarad, but 1 millifarad would be pretty much like having in parallel two 500 microfarad capacitors. I could do that as well if you want to. So when we rerun the simulation, now because we have so much capacitance, you can see that, okay, so let me see. Okay, I was forgetting this one. Now that we have so much more capacitance, twice as much, because I have 1 millifarad, you can see that from before, from having like my minimum value to pretty much 9 volts, as you can see in here, it was going down to 8.8 volts, as you can see right here by the cursor, right on the top. Now by doubling my capacitance, I was able to improve dramatically, okay, my minimum value. So that means that my average voltage was able to go higher. Okay, so we're going to continue here on capacitors. Hopefully you can see my screen, no problems. So, and what we are going to discuss about capacitors today is AC circuits, of course, and it says here AC circuits, but we are going to be using the capacitors for a DC circuit. It's still the same idea. The difference is going to be that in AC circuits, we are going to use non-polarized capacitors, while in DC circuits, we have to use polarized capacitors, okay? When we want to have a high capacitance in the circuit. And yes, we can use non-polarized capacitors in DC circuits as well, and you are going to be using those in the future, but they don't have as much capacitance as the counterpart, which is the electrolytic capacitor. So we're going to discuss pretty quickly which are the 3 factors that determine capacitance. When we think about the word capacitance, I want you to relate that word to capacity, meaning how much, like this word means, how much energy I can store in a field. That's what it means. How much energy we are going to be able to store in the electrostatic field. And the reason why is called a electrostatic field. Electrons, static, not moving. Electrons that are not moving and are fixed in place between 2 plates, okay? And they stay put just like a charged battery because there's an attraction between the positive and negative terminals. But we'll get to that in just a moment when we discuss the electrostatic charge that we develop in the actual capacitors. And then something else that we are going to do is that we are going to get into doing some calculations today. I mean, if we don't do calculations, what's the point, right? And in this case, we are going to discuss how to calculate the RC time constant in a capacitor, and also values called series and parallel connections of capacitors. So let's get to this because we only got like 20 minutes left. So what are capacitors used for? In level 2 theory, you are going to learn that capacitors are widely used for this, for power factor correction. So have you covered already power factor in theory? No, not yet. But that's something that you are going to cover in the future. And you are going to be able to cover like power factor and efficiency, like in, let's say, in a motor. And you are going to be learning how is it that a capacitor can help you to have a power factor which is equal to 1. So I'm not going to get too deep into capacitors because I'm pretty sure that your theory teacher also is going to brush on the same topic. So you are going to be getting the same lesson twice. And for the sake of your own time, it is better just to cover what's really important for electronics only, okay? So this is the important part for us. Storing an electric charge to produce a large current pulse. That's what's really important to us, because that's what the capacitor is doing when we connect it, listen to this word, in parallel with the load. It always has to be connected in parallel with the load in our class, okay? Not in every scenario. Just for our projects, it will be a parallel connection, because what we are doing is that we are connecting this capacitor in parallel to charge, okay? And once it's charged, it's going to be discharging over the load that is connected to it. And in today's class, we are going to see, and this is something that you are going to see in the future, how we connect a resistor in series with a capacitor in order to delay the amount of time that it takes to charge the actual capacitor. And by doing that, by connecting a resistor in series, we create a timing circuit, because we can manipulate how much time we want the capacitor to take to charge. Okay, so, and then this other word here, electronic filter, is the same thing that we are doing when we are storing energy. We are just filtering our DC. Okay, so this is what we are doing pretty much in this class as well. So let's keep moving. So non-polarized capacitor are used in AC and DC. I already said that before. And polarized capacitor are used in DC circuits only. And it's important to connect them in the proper polarity, positive to positive and negative to negative. So if we have a load here, okay, like if we have a load here, and we are going to be connecting a capacitor here, is very, very important that if that is the positive terminal, and this is the negative terminal, that we have the same polarity on both. And I already told you what's going to happen if we don't do that. We're going to see lots of oil. Okay. So now, how will the capacitors build? The capacitor is just two metal plates which are separated by a dielectric material. A dielectric material is just a material that is very, very thin. It's paper thin. And it has the ability to isolate the two plates. So by doing that, what's going to happen is that we are going to be able to remove electrons from one of the plates and deposit those electrons in the other plate. The plate that loses the electron is going to become positively charged, and the plate that gains the electrons now is going to become negatively charged. Even myself, when I say that, sometimes is something in my mind says, wait a minute, it doesn't seem to be right, because, okay, so the one that is losing is going to become positive, and the one that is gaining is going to become negative. Like in my mind, that's counterproductive, like that word. But that's the way it is, because it means that we have more particles with a negative charge, which are electrons. When that happens, once the capacitor is charged and the capacitor has reached source voltage, like if the capacitor, let's say, if this one is rated for 120 volts, if that's the rated voltage, and you connect it to a 120 volt source, once the capacitor has reached that 120 volt charge, then no any more motion of electrons happen. Now that we have all these electrons, and I'm just gonna try to use here like a little circle to show electrons. Now that we have this bunch of electrons here, and you were gonna see this anyway in the next couple slides, but I wanna show you this way anyways. Now we had a bunch of electrons here. Now those electrons, at the very same time, we have on this side a bunch of holes. And what happens? All these electrons want to move back home. All these electrons know that they were departing from that plate, that is their home, and they want to go back home. What is the problem? That because the capacitor is charged, because the capacitor now has this potential difference across its plates, if nothing is connected to the capacitor, they cannot go anywhere. However, there's going to be a very heavy force of attraction that is going to occur between the capacitors. So right here, you are going to have like a bunch of lines of force through the dielectric material, because the actual electrons, they are trying to move back to where they came from. So they are trying to go back to here, and that's why that the dielectric material, it doesn't allow the electrons to pass through, and that's why that the charge stays put inside that field. Okay, so as I said before, it's an electron static field. It is a field which is filled, if you want to think of, with electrons that want to move to another zone, that want to move back home, but they cannot because of the dielectric material. And of course, because there's no perfect dielectric material, you may wonder, so does that mean that a capacitor can stay charged pretty much for 1,000 years? In theory, they should be able to stay charged for 1,000 years. However, that's not going to happen, because no any dielectric material is perfect. And over time, there's going to be a bunch of electrons that are going to be moving through the dielectric material. They are going to be moving, a small amount of electrons are going to move through the dielectrics, are going to find their way back. And the capacitor eventually, over time, is going to discharge naturally, because no any dielectric material is perfect because of that. And you may wonder, okay, so how long? Well, that's going to depend on the quality of the dielectric material. And further along in this lesson, you will see that different type of material like mica or glass or sand or oil, castor oil, has different dielectric properties as well. So this is what I was explaining to you just recently. And this is just to refresh your memory, okay? So here we have a negative charge. Here we have a positive charge now, okay? And that happened because we connected, like when we connect a power source, we are gonna be like removing, like you can see that this positive terminal is gonna be attracting all the electrons from this plate, and then the electrons are gonna move to that positive terminal. Okay, and all these excess electrons that came to the positive terminal are gonna be pushed to this other terminal here. And the dielectric is not going to allow the flow through it, and that's what's gonna keep the capacitor charge. I already said that twice. Any questions so far? Now, right at the beginning, okay? When we start to charge the capacitor, of course, like if we had a voltmeter here at the power source and another voltmeter at the capacitor would be reading 0, but over time, the capacitor is going to charge. And the way, I mean, like, something which is important to know is that, like, if you think about it, right at the beginning, we are going to have a very large inrush current. So if I were going to connect here an ammeter, then right at the very, very beginning, let's say, of course, this is like 0 volts here. This is the max voltage here. By the way this looks, we can see that this capacitor is already charged, and that's why that the battery and also the capacitor have equal voltage. But let's say that the capacitor is not charged. When the capacitor is not charged, right at the very beginning, if this is an ammeter, and that's what it is because it's connected in series, okay, like right at the very, very beginning, the amperage is going to be to its max value when we start to charge the capacitor. As the capacitor charges, then the amperage starts to slow down until the amperage goes to 0 value. And you may wonder, well, why does that happen? Simple enough. Right at the very beginning, when the capacitor is discharged, we are going to have a very large flow of current flowing through the wires to charge the capacitor. But as the battery and the capacitor reach equal potential difference, then the amount of current that will continue to flow through the wires is going to diminish. And when they have the same potential difference, then there's not going to be any flow of current through the wires anymore. So that's why that current will drop down to 0. So I'm just going to skip a couple slides ahead, and you have the freedom to go ahead and check and look at this anytime you want. Okay. So the current in the capacitor is going to be able to flow only when the capacitor is either charging or discharging. And this, what you see on this slide here is what I was telling you before about the leakage. Okay, electrons eventually leak through the dielectric material. And this is called, and that's going to be a test question, so please keep that in mind, that is called leakage current. What is it that determines capacitance? Capacitance is going to be determined by 3 things. Number 1, the area of the plates. So the key word here is area. The bigger the plates, the more electrons that we are going to be able to have. Area of the plates is one of the themes that determine capacitance. The other one will be the type of dielectric material. Okay, so if we go one slide back, you can see that the dielectric constant, which is equal to 1, our reference point will be air. And then different materials like bakelite or castor oil, they have different dielectric constant. What does that mean? That means that they have a higher resistance. Okay, so they can produce a capacitor that can store a higher charge between its plates because it developed less leakage current. So I already told you like 2 of the factors. And the third one, you may wonder, so, okay, so what is the third one? Is the area of the plate, number 1. Number 2, the type of dielectric material that we use. And the third one will be, what do you think it is? Do you want to guess? The distance between the plates. So the closer, we have a capacitor here, okay? So the closer these plates are, the more charge that we can store, because in that instance, we are going to have a higher electrostatic attraction between the charges in the actual plates. Then we already said three factors, okay? Area, distance between the plates, and dielectric and the type of the dielectric material. Now, let's move into calculations, guys. Calculation time. So when we have a capacitor that is connected in parallel, and this is a very straightforward, capacitance in parallel is calculated by adding all the capacitors that we have connected in parallel. And so if you want to see it, you can see it as storage tanks. Okay, so if we have a storage tank here, and in this case, our tank is 110 microfarad, and this other tank here is 20 microfarad, and this one is 30. And that microfarad number refers to the capacity that they have to store a charge in the electrostatic field, okay? C1 is 20, 30, and 60. So the total capacitance is going to be equal to 110 microfarads. When we connect capacitors in parallel, what we are doing in reality is that we are increasing the area of the plates. That's why that capacitance increases. On the flip side, when we connect capacitors in series, and now we have the same capacitors, but they are connected in series, our 20, 30, and 60, now it's going to give you a total capacitance equal to 10 microfarads. And the reason for that is that the distance between the plates, it is increased. So the distance between these two plates, that distance is going to be adding up to that distance and adding up to the third capacitor. And because we have increased the distance between the plates, we have decreased our electrostatic attraction. Now that we have less electrostatic attraction, our total capacitance is going to decrease. And by using the reciprocal formula, we can find what's going to be the value of those capacitors connected in series. I know you may wonder, so what's the point of connecting capacitors in series if we are going to be reducing our capacitance? So this is the opposite of parallel and series resistors. So in the case of capacitor, the formulas are backwards. I'm going to wait just a little bit before we get into this topic, because this is project 7 in the shop, okay? So in project 7, when we are getting ready for that, we are going to see like the charging time of a capacitor and also the discharging time of a capacitor. And we are going to be using what is called time constants. And we are going to be able to use this formula in order to calculate the charge time for a capacitor and also like the discharge time. I want you please to go through this complete PowerPoint. At least in our class, we're not going to be using anything which is color-coded. The value for all the capacitors that we are going to use, they are printed on the actual capacitor, okay? So we don't have to worry about any of those. And that's not going to be tested either. Make sure, whenever you have a chance, make sure, please, to go back to Cont'd. And on Cont'd, under the content, you see a tab which is called Lab Simulations. Under Lab Simulations now, you also can see project number 4, and that's what I was using this morning. And as soon as you click on this link, it's going to open FileStat for you, and you're going to be able to do your simulations. And you can play with it, okay? Like if you want to play with it and say like, whatever, I want to change this to 50 microfarads, let's say, to see what happens. Okay, without load, nothing's going to happen. But even at 25 watts with 50 microfarads, we're going to have like a very awkward signal. Let's put it back to normal, apply it. And then you can see the difference right there between having low capacitance and high capacitance, even for the same load. And with such a small load, would I be able to get an even better signal? I would be able to get almost a perfect signal. You know, still with a little bit of ripple, but almost a perfect signal. The last thing that I want to mention about this is that when we have our capacitor in the circuit, how much do you think is going to be the amount of ripple voltage that we are going to have in the circuit? Actually, like by using this formula, you can see that V peak, which is the V max minus the V minimum, divided by 2 times 0.707, that's going to give you the ripple voltage, which is the amount of AC voltage that we have in our rectification circuit. But when we filter, and this is what this is called, when we filter the signal and we don't have any load connected, the amount of ripple voltage, of course, is going to be 0. We're not going to have any AC voltage. And that ripple voltage is going to increase depending on 2 things. It's going to decrease if you increased the capacitance, and it's also, and then the ripple voltage is going to increase, and you increase the load. So right here, we are going to have way less ripple. Okay, while here, we are going to have like a huge ripple. So right here, without any load, the ripple voltage is going to be 0. Right here, with a little bit of load, that was the 25-watt light bulb, we are going to have a little bit of a ripple voltage. Right here, with the 660-watt load, then we are going to have a lot of ripple voltage. So have a nice day and blessings for you all.